So, in the previous lecture, based on the equation for Pearl-Navarro stress, we saw that there are certain crystallographic constraints, and using those crystallographic constraints we can describe which particular planes the slip will take place, and it can also describe which particular direction the slip should take place. And we found that qualitatively what the relation says is that the planes should be densely packed planes, which would in other words mean that they are the interplanar spacing is largest. And so, we set on to look for the interplanar spacing for FCC, and we looked at three low indices planes which are most likely to be the which are most likely to have highest interplanar spacing. We looked at 111, 100 and 110, and we found number of atoms which is here in the simple cubic cell, and the atoms per unit area, calculating the area. So, the atom divided by the area, and we also calculated what is the distance between the atomic planes. So, looking at this number, here we want what is the highest density. So, we found that 111 in the FCC system has the highest number of atoms per unit area. On the other hand, for the planar spacing also it has to come because the density, overall density has to be constant. So, if the plane has the highest density, the interplanar spacing will have to be largest, and therefore, it turned out that the interplanar spacing for 111 plane is the largest, which is A naught by root 3. So, now what we want is to find out what is the Berger vector. Now, for the Berger vector we saw that for the Berger vector what we need is the closest packed plane direction. Now, which will be the closest packed direction for the FCC? Now, if you look at this diagram, or if we draw the usual diagram where we have the atoms touching in the, so here it is more like a point. So, it is described as a point. Here they are drawn, the atoms are drawn more like a sphere, and when we look at this we know that the closest direction has to be like this, or let me use a different color. So, you can see the atoms are touching along this direction, which is 110. So, along the 110 direction we see that the atoms are touching. So, this has to be the densely or the densest packed direction, and therefore, B for FCC should be 110, and therefore, for FCC what we see is that the slip system consists of 111 plane and 110 direction. So, you can see that the relation for the shear stress, Pearl-Navarro stress, has given us more information about the slip directions, which is the most likely slip plane and which is the most likely slip direction. Now, let us do the same exercise for BCC. So, again we will take three particular planes which are most likely to be the densest packed planes. And now, what we need to do, again like the previous time, we will draw the unit cell, BCC unit cell, and we will now assign atoms where they belong. And let me draw this back plane so that I can draw the atoms in this corner and also at the center. So, we have these atoms inside the BCC. Now, here which is the plane. So, the plane 111 plane is this one, and what you will see is that this particular center atom is not really on this BCC plane. Even the other sorry is not this 111 plane, even the other 111 plane that we draw, it becomes clear that this central atom does not lie on any of these 111 plane. In fact, it lies on a altogether third plane, which is itself formed by body centered atoms of 3 different cells. So, here you have cell, here you have atom, here you have a body centered atom, and these 3 together form another 111. So, here you have one additional 111 plane which contains atom, which is in between these two 111 planes. So, there is first thing to understand is that there is one extra 111 plane in this BCC, and for this BCC 111 layer, now you can see that the number of atoms for this particular plane is 1.5, and therefore, atom per unit area will be 3 by 2 divided by the area, which is root 3 by 4. A root 2 is the sides of the triangle square, and therefore, it comes out to 1 by root 3 A naught square. Now, let us calculate the distance between the plane. So, the total distance from this atom to this atom is A naught is actually root 3 A naught, and in that we have 3 into 2 number of planes. So, it comes out to A naught by 2 root 3 distance between the planes. Now, let us come to 110, which is this particular plane. For 110, you would be able to see that the number of atoms is 1. We are talking about 100, which is this one. So, here the number of atoms is 1, and the area by which we have to divide is A square. So, this is the A square area. So, this is 1 by A square, and the spacing with here is from here to here, which is A naught by 2. Then we have 110 atom, sorry 110 plane, which is this one, and here you would be able to find that this also contains one body central atom. So, here there are 2 atoms, and the atoms per unit area will become 2 by root 2 A naught square, because this is the area root 2 A naught square, which is equal to root 2 by A naught square, and the spacing between the planes would be A naught by root 2. So, here what do we see, which one is the for BCC, which is the plane which contains the largest density of atoms, and it will not be very difficult to see that it is actually 110. So, this is 110 for BCC, 110 is the densest plane, which implies that interplanar spacing is largest. So, you can see this quantity is the largest amongst all 3. So, again we are able to derive what is the plane on which slip will take place based on the constraints that we obtain from the Pearl-Navarro stress. Next is the Berger vector. So, now let us talk about the Berger vector. Again what we are looking at is the closed pack direction. For FCC we saw that the atoms touching the or the direction in which the atoms touched were around 110, but in BCC there is no atom in the phase center. Instead here the atom is in the body center, and therefore, the atoms touching is in this particular direction, which is 1 1 1, and therefore, here the closed pack direction is 1 1 1, and what we get is that for BCC 1 1 0 and 1 1 1 is slip system. In fact, we have not looked at another plane which is also a possibility, and it has been known to be also a slip plane for BCC, which is 1 1 2. So, 1 1 2 1 1 1 is also a, you can do the exercise for 1 1 2 and find out what will be the atoms per unit area, distance between the planes and so on. And you would see that although it is not as high as 1 1 0 in terms of density, but it is also, it just also happens to be the slip plane for BCC system. Now, here what you would realize that any particular 1 1 1 direction in BCC is actually contained in several 1 1 0 planes, several 1 1 2 planes, and something I should mention here at this point, that there is another one here, it is 1 2 3. So, BCC is a complex in sense of mathematics, but it makes the dislocation movement easier, because you have not just one set of planes like in FCC, here you have 1 1 0, 1 1 2, 1 2 3. So, because of other factors 1 1 2 planes and 1 2 3 also become a slip plane, although 1 1 1 still remains the slip direction. And for each 1 1 1 direction, it is contained in several of 1 1 0, 1 1 2 and 1 2 3 planes. Which makes the slip of BCC dislocations much more agile, meaning it can move much more easily, and therefore, what we observe what is called as pencil glide. So, we will come to this again later on when we talk about slip, and then later on again when we talk about specifically about BCC systems. So, this different systems, and particularly the fact that 1 1 1 1 direction is present in several 1 1 0, 1 1 2 and 1 2 3 planes, leads to pencil glide in BCC. And since we are talking about how many planes are contained, so let me come back to this BCC system. We said that there are 1 1 1 plane and 1 1 0 direction, and here there is no ambiguity, there is only these planes and this direction which form the slip system. So, how many 1 1 1 direction are there? There are 4 1 1 1 planes, and we will see this is something becomes much more clear when we look at what is called as Thomson's tetrahedron. So, there are 4 1 1 1 planes, and each 1 1 1 plane contains 3 directions of 1 1 0. This slip system is very easy to visualize using what is called as Thomson's tetrahedron, and again we will come to this when we talk specifically about the FCC system. Right now we are just we came to this topic while looking at Pearl-Navarro stress and so on. So, now we have looked at the Pearl-Navarro stress and how its understanding leads to constraints which gives us that which are the particular systems where slip will take place. And although in BCC it predicts only 1 1 0, 1 1 1, but it has been observed that slip also occurs in 1 1 2 planes and 1 2 3 planes. Next, what we want to do is we have looked at several mathematical relations. So, why not try to do some examples. So, next step is trying to solve some examples. You remember we talked about the image dislocations. So, in the image dislocation, let us say we have taken a single whisker. Now, it is a metal whisker where dislocations can easily move, and it is given that for this material G is equal to 200 gigapascal. So, it is something like a iron. Berger vector is equal to 4 angstroms, nu is equal to 0.5, which is the ideal Poisson's ratio, and you are given that the minimum F by L required for the dislocations to move, or which describes the Pearl-Nabarro valley of stress, is 1.02 Newton per meter, and it is given that the diameter of this whisker is 100 nanometer. So, let me use uppercase D. Now, what you need to find out, the thickness of the cell of the whisker which is free of dislocations. So, this is the question, this is what you need to find, meaning you have to find this shell. So, this is the thickness outside, meaning you will on the surface you would look at it something like this, and there is thickness outside it where there is no dislocation. And why is there no dislocation? If you remember, so if there is a dislocation somewhere over here, then it is always experiencing a force which is which is as if there is a negative dislocation at a similar distance outside the surface, and it is causing a attractive force onto this dislocation to come out to the surface. And therefore, when this force exceeds this minimum force required for movement, then this dislocation would move and it will anneal out. So, if this is the if at this particular distance a dislocation experiences a force which is higher than this force, then beyond this distance all the way up to the surface, you can imagine that this force would be the force acting on the dislocation would be higher than this F by L, and therefore, all the dislocations outside this particular depth would anneal out. Assuming that first there is one more assumption, that all the dislocations are located horizontally. If they are located in a direction where the motion path of motion would become something like this, then climb would have to be involved or the distance would become larger. So, an inherent assumption in this problem is that all the dislocations are such that they can move horizontally with respect to the geometry. So, now what we need to find is this D. What is this thickness of the cell D? So, what we know that a force Fx by L acts onto a dislocation which is the image force. So, this is the image force. I am writing image force, but there is no distinction in the force, it is still a force acting on the dislocation. So, Fx by L is equal to minus Gb square by 4 pi 1 minus nu d, and this minus sign is just telling that one of the Berger vectors is negative in sign, but the force is still attractive, meaning the dislocation would move in this direction. And this d is this d. So, this is the distance that it is away from the surface, this is the largest distance at which this dislocations will be able to move. So, if it is the largest distance, this is where the force is the smallest, the image force, and this smallest force must still be equal to 1.02. So, we will say that this is equal to 1.02 Newton per meter, and then what we need to do is D is equal to 200 into 10 to the power 9 into 4 square into 10 4 is, this is 4 angstrom. So, 10 to the power minus 10 into square is 10 to the power minus 20 4 pi and nu is 0.5. So, 1 minus nu is 0.5 and this comes to denominator. So, this is 1.02 and when you do the calculation you would find that this is equal to 5 nanometer. So, the shell of thickness 5 nanometer, which means that the overall diameter, if you look at it, is 100 nanometer. So, the only the 90 nanometer diameter contains dislocations and outside it there is 100 there is another 10 thickness of 10 nanometer including both the sides, which does not contain dislocation. So, although this whisker is not completely dislocation free, there is a large fraction in terms of radius itself, it is 10%, which becomes larger when you consider the area and volume. So, a very large fraction of this whiskers is dislocation free. So, if you look at the strength of this shell is much higher and this particular region inside it is, you can assume that it has the similar strength as a bulk material, which is also not true, but for now let us assume that the inside component has the same strength as the bulk material, but the outside has much higher strength. So, even in that condition, given that this is a large fraction of the whole whisker, this will have very high strength, not anywhere close to the theoretical strength, but still much higher than the total strength of the bulk material, and this is what gives rise to such high strength of whiskers. So, here for in this example we had the 100 nanometer whisker where only 5 nanometer of the cell outside it is dislocation free, but still it will have very high strength. So, whisker we have not calculated a strength. So, I will just write whisker can be expected to have very high strength, given that a large fraction of it is dislocation free. So, this is one example which is related to the force acting onto it. Let us solve another example. Here you are being asked to calculate force. When I say force, I mean you have to calculate Fx, Fy, Fz using the Peach-Kohler relation. What you get is the vector quantity. So, it will have all the 3 components. Now, you have to calculate it on a screw dislocation, and it is given that the Berger vector is, so for to make your life easy, it is given as 0 0 1, and if it is given the Berger vector 0 0 1, you can also say that the line vector is also 0 0 1 or it is negative. And where is the stress arising from? It is due to an edge dislocation. So, in order to calculate the stress due to this edge dislocation, we also need to know their geometry, and it is given that E is equal to 0 0 1. What you will notice is that the Berger vector of this edge dislocation is not given. So, it looks like something is missing. So, let us see if we can find out this missing quantity. Now, if you remember when we were deriving the relation for, not deriving actually, when we looked at the full form of the Peach-Kohler relation, which is sigma dot cross B, which F by L is equal to sigma, which is a tensor quantity, dot product with Berger vector and cross product with line vector. So, we wrote down the full form of this equation, and over there we solved some, or we tried out some simple problems. Over there we were looking only at force on edge dislocation because of an edge dislocation. We have not yet considered a screw dislocation. I just said in passing that in a screw dislocation it would be a little different. So, this is what we will experience here. Now, here we are seeing that we need to calculate the force onto this screw dislocation. So, this is our dislocation on which force is to be calculated. and the stress is arising because of a edge dislocation. So, this is the edge dislocation because of which there is stress field. So, this screw dislocation is at some distance x and y from the edge dislocation, which is causing this stress field, and we are given 0 0 1 line direction for both of them. So, that is why I have drawn it like this. So, this is the screw dislocation with its direction going into the plane. Similarly, the direction of the edge dislocation, which is causing the stress field, its direction is going into the plane. But what we are not given is, like I said, the Berger vector for this dislocation. We know the Berger vector for this because it is a screw dislocation. So, Berger vector will be in the same direction as the line vector or its opposite of it, but anyhow we are given 0 0 1 and 0 0 1. So, they are both parallel and not anti-parallel. So, what do we need over here? So, let us go back and recall what was sigma dot b in the full fledged form. Sigma dot b, if you remember, if you write all the quantities assuming no particular kind of dislocation. So, we assume that all the 9 quantities in this tensor are available, then it comes out to be, and assuming that again this Berger vector is also not 0 0 1, but b 1 b 2 b 3 where all the 3 components exist, this comes out the way So, this is something I have already written earlier, but for the sake of completion I am writing it here again, and it will help you visualize what should be the final form of the answer. And if sigma dot b is this, we also showed that sigma dot b cross E is equal to there is a bit of repetition here, but I hope this will be useful for you, so that you know exactly what are the specific steps that are needed to calculate or solve these problems. So, what you need to do is first write down the general form of the equation. So, this is epsilon 3 or eta 3, eta 2, eta 1, eta 3, eta 2, and this is eta 1. So, this one is the expanded form of the sigma dot b cross E. All you need to do now, you already know what are the sigma components that is present because that is the edge dislocation. You also know what is the b and E, which is because of this, and then solve it. Okay, so, I will end this lecture without solving it and leaving it here, and I hope you can come back and you can solve it. So, we will meet in the next class.